Today we study the integrability of functions and define the integral over a subset of Rn more general than the rectangles. We discussed integral over rectangles last time. First we study the continuity and the integrability. Okay, so in the study of integral of single variable functions, we know that continuous functions are always integrable. This is also true for multivariable functions defined over a rectangle. Okay, so this is the theorem. F defined over a rectangle I continuous. And then the conclusion is that F is integrable over the rectangle I. Okay, so this is the generalization of the corresponding result for single variable functions. Okay, so the proof is also following the same ideas for single variable case. So the rectangle I is a bounded closed subset. Therefore, as a continuous function defined over the sequentially compact set, the rectangle, our F is uniformly continuous. Okay, since I is sequentially compact, F is uniformly continuous. Therefore, for any epsilon positive, we can find a delta positive, such that the value of f x and fy less than epsilon if xy are points in the rectangle which distance less than delta. Any two points in the rectangle xy, if the distance from x to y is less than delta, then the value, the difference of fx and fy will not exceed epsilon. Okay, so the rectangle, we can divide the edge of the rectangle by k equal subintervals. Okay, so this is k subintegral interval, and this is also k intervals. Then the diameter of the subrectangle will be small as well. Okay, so divide the edge of I into k equal subinterval. So we obtain a partition of I of the rectangle. Okay, so this partition is P, a partition P of I. So if K is large enough, K is very, very large, that is, we divide the rectangle to be many pieces, smaller and smaller. Okay, so if K is large enough, for any sub-rectangle belonging to the partition P, that is this rectangle and this. Okay, if the K is very large, then the diameter of this rectangle, we have the diameter of J, which is the supplement of the distance from x to y for any 2 points x, y belongs to J. This diameter will less than delta. As k increase, the diameter decrease. Eventually, it will less than delta. The delta is the number we determined using the uniformly continuity of f. Okay. So for such a partition, for x, y in J, because the diameter is the supplement of the difference from of the distance from x to y. Therefore, because the diameter is less than delta, so the distance from x to y will also less than delta. Consequently, fx minus fy, the absolute value of fx minus fy will less than epsilon. So the corresponding oscillation of f over the subrectangle J, that is capital MGF minus small mgf. This is equal to by definition the supplement of f over J minus the infiniment of f over J, and you can prove that this is precisely equal to the supplement of x, y in J. Fx, absolute value of fx minus fy. So this will not greater than epsilon. This will not greater than epsilon. Therefore the upper sum, the difference between upper sum and the lower sum, I have no space to write here. I will write in this page and in the upper boundary, near the upper boundary, and write in red. Okay, so Fp upper sum minus lower sum, that is the summation over all rectangle capital MGF minus small mgf, then the volume of the rectangle J. But because in the last line of this page, we already saw that the capital M, all the capital M minus small m will not greater than epsilon. So this capital MGF subtract small mgf can be controlled by epsilon, and then we move the epsilon out of the summation. This will less than the epsilon, the volume of all the J. But the volume of all the sum of the volumes of the all the subrectangle J is precisely the volume of our initial rectangle I. So this is precisely epsilon vi. Okay, so using the uniformly continuity, we obtain the following conclusion. For any epsilon positive, we can find a partition P such that according with respect to this partition, the upper sum minus the lower sum, the difference between upper and lower sums will not greater than this small epsilon multiplied by a constant. The constant is the volume of the rectangle I. So in other words, the difference between the upper sum and the lower sum can be arbitrarily small. We can as long as the partition is fine enough. That is, if the k is great enough, k is large enough, we can ensure that the difference between upper and lower sum will be very, very small as we want. So by our previous theorem, the if and only if condition for integrability, we conclude that our f is integrable over the rectangle. So proving this theorem. Okay. Now in our next result, we will give some more general criterion for testing the integrability of function. This theorem says that continuous function always integrable, but if a function is not continuous, can it be integrable? Okay, we will solve this problem. So to study this problem, we need a important concept. So a subset S of Rn, we say that this subset has Jordan contain 0 if for any epsilon positive there is a sequence of a rectangle denoted by I1, Im, such that the first requirement is that the union of these rectangles contains our S. That is, the rectangle is a cover of our subset S, and the total volumes of the rectangle is small. That is, if no matter how small epsilon is, you can always find a sequence of finitely many rectangles I1, I2, Im, so that this finite number of rectangle covers S, and the total volume is smaller than the given epsilon. In this case, we say that our subset S has Jordan content 0. Okay. So this is a very natural definition. If the set has Jordan content 0, it can be considered as small in some sense. Okay, and the basic property of Jordan content 0 is the following. The first one is very obvious. So if another subset S is a subset of S, then T also has Jordan content 0. This is obviously true. The next result is not so obvious, but the proof is not difficult. If we have finitely many subset which Jordan content 0, S1, Sk has Jordan content 0, then the union also has Jordan content 0. Okay, so this is the second property of Jordan content 0 we need. The proof of the second property is very easy. So because every Si has Jordan content 0, therefore for any epsilon positive, for every I, we have some rectangles I1, Im, such that the Si is contained in the union of Iij. The union is taken over the sub index j, and also the total volume of this M rectangle is small as we wish. We can declare it to be smaller than epsilon over k. Okay, but I will remind you that for different I, the number of rectangle you need might be different. Okay, therefore maybe we should write that is the number small m depends also on I. So we had better replace this by mi. That is the m here. The m here should be mi. For every si, the number m might be different. So you had better write m as mi. Okay. So I have already modified my presentation, my writing. I intensively to write it without the sub index I, just to remind you. Now I have add I here and here. Okay, so you should be careful about